one instance. Next, third unit, 2D transformations. So what is a geometric transformation? The operations that are applied to the geometric description of an object. So to change its position and orientation or size, these are called as the geometric transformations. That is, you can change the operations of the particular geometric objects. That is, it may be position, or it may be orientation, or it may be size, is called as the geometric transformations. Okay, see, these are the different type of the transformations. That is the transformations, scaling, rotations, likewise. Okay, so in the transformations we have different operations. There is a scaling, rotations, transform the objects into one place to another place, like that. See, here we can define the different type of the applications, that is animations, image or object manipulations, viewing transformations, etc. So these are the different type of the application, that is animation, image object manipulation, viewing transformations. See, given a 2D object, transformation is to change the object, that is position, size, orientation, shapes. So these are the different type of the transformations in the two dimensionals. That is, first one is the translation, are also called to change the position of one place to another. Okay, second one is the scaling. That means we can change the size of the particular object. It may be increase or it may be decrease. Next, orientation, that is rotations. We can rotate the particular x and y axis. Next, shapes, shear, that is we can entirely change the shape of an object. Okay, so these are the main transformations of the particular two dimensionals, that is translation, scaling, rotation, and shear. Okay, apply a sequence of matrix multiplications to the objective vertices. So now you can apply these all the matrix multiplications to perform the operations on the particular objects. Next, how we can represent particular points. See, we can use a column vector, that is a 2 by n 2 by 1 matrix, to represent a 2D point, that is a modulus of xy. So actually we have defined the general linear equation, that is a general form of linear transformations, that can be written as x dash equal to ax plus by plus c, or y dash equal to dx plus ey plus f. That is x dash y dash 1, that equal to a b c d e f 0 0 1 and x y 1. Okay, so a general form of linear transformation can be written as x dash equal to ax plus by plus c, or we can define as y dash, that is dx plus ey plus f, or in the matrix transformation you can define x dash y dash 1, that is a constant, that equal to a b c d e f 0 0 1 into x y 1. Okay, so likewise we have to represent the points on the particular 2D dimensionals. So first one, the translation. So that means we position a point along a straight line. So now based upon this translation we can change the position of the particular object. That may be line, that may be curves, that may be ellipse, whatever may be, or that may be object. Simply we can say objects. So reposition a point along a straight line. Next, given a point x comma y and the translation distance tx comma ty, that is we can take the coordinate values for x and y and define the distance of the particular translations. We can define the x and y. See, likewise. So likewise, so the new point equal to x dash comma y dash. So x dash equal to x plus tx, y dash equal to y plus ty. Okay, next, or we can define p dash equal to p plus t, where p dash equal to x dash y dash, p equal to xy, t equal to tx ty. Okay, so There is a translation, there is a reposition of the point. That means how we can change the position of the particular object. So based upon that, we can calculate the different type of the new points, that is x dash equal to x plus tx and y dash equal to y plus ty. Okay, or we can take the formula, that is p dash equal to p plus t, where p dash equal to x dash y dash, p equal to xy, t equal to tx ty. Okay, how we can translate an object to multiple vertices? So now we can see here. For example, we can take an object, that is an object, for example, so now we can change the position, that is we can translate individual vertices. This is the one vertex, 2, 3, 4. So completely we can change likewise. So we can change the that means we can translate the individual vertex to one position to another position. Okay, next one. So rotation center, that is origin of 0 comma 0 n, so 0 comma 0. Now theta greater than 0, rotate counter in clockwise. Theta less than 0, rotate in the clockwise. Okay, that is anti-clockwise and clockwise. Based on clockwise and anti-clockwise, we can define that ones. Okay, x comma y, that is rotate about the origin by theta, that is x dash comma y dash, and x dash y dash is like that. There is a x comma y. Now we can change x dash comma y dash. Okay, see, x comma y implies rotate about the origin by theta, that is x dash y dash. Now we compute the x dash y dash, that is x equal to r cos of phi, y equal to r sin of phi. Then x dash equal to r cos of phi plus theta, y dash equal to r sin of phi plus theta. Okay, so likewise we have to using of different type of the equations, and we can rotate the particular object one place to another place. Simply we can rotate clockwise or anti-clockwise. Okay, see, so x equal to r cos phi and y equal to r sin phi, and x dash equal to r cos of phi plus theta, y equal to r sin of phi plus theta. So x dash equal to r cos of phi plus theta, that is r cos of phi cos theta minus r sin of phi sin theta, that equal to x cos theta minus y sin theta. Then y dash equal to r sin of phi plus theta, that is r sin of phi cos theta plus r cos of phi sin theta, that equal to y cos of phi plus x sin of theta. So x dash equal to x cos theta minus y sin theta, y dash equal to y cos theta plus x sin theta. Then matrix form x dash y dash equal to cos theta minus sin theta cos theta, that is equal to xy. So how to rotate an object with multiple vertices? See here. So likewise we have to rotate different type of the object. See, this is the square. Now we can change this object may be change into the this, that is rotated into this position, that is anti-clockwise like that. Okay, so we have to rotate individual vertices, then it will be change the, that will be rotate to the all the vertices. Okay, so in that way we can rotate the particular object, it may be clockwise or anti-clockwise based upon the conditions. Okay, next, scaling. After alter the size of an object by a scaling factor sx comma sy, that is x dash equal to x into sx, y dash equal to y into sy, that implies x dash y dash equal to sx 0 0 sy in x comma y. See, in the scaling we can change, we can increase the size of an object. See, for example, we can take values of x comma y 1 1, x1 y1, x2 y2 2 2. So this is an object. When you take x equal to y equal to 2, that is x comma y equal to 2, that is x1 comma y1 equal to x2 y2 equal to 4 comma 4. Now it will increase the size of the particular object. Okay, so simply we can say we can alter the size of an object by a scaling factor, that is sx comma sy. So based upon that we can calculate x dash equal to x into sx, y dash equal to y into sy, that is x dash y dash that equal to xx 0 0 sy, that is xy. Now we can change the values, now we can change the particular size of an object based upon the scaling factors. See, not only the object size is changed, it is also moved. After whenever it will be assigned the change, but also it will be transformations also it will be done in the scaling. It will be object will be increased and translations also applied. Okay, so because of it will be size is changed and also it will be moved to one place to another place. Okay, see here 1 1, but here the 2 2, now it will automatically change the area of the position. So usually this is an undesirable effect. We will discuss the how it will be fix the particular problems. Okay, so this is the scaling. Scaling minus 1 comma 1 define the likewise, and scale 1 comma minus 1 define likewise. So that is xx minus xy, x minus y minus x minus y comma minus y comma x. So based upon that the scaling factors will be change the objects, and it may be x-axis and y-axis, that may be minus x and minus y. So likewise it will be changing the particular scaling of the factors. See, put it all together, that is the translation x dash y dash equal to xy plus tx ty. So based upon the t equation, we can translate the objects. In the rotation, that is x dash equal to cos theta minus sin theta tx, y dash equal to sin theta cos theta ty, and scaling x dash y dash equal to sx0 0 sy tx ty. So based on these equations we can translate the object, we can rotate the object, we can scaling the objects of the based upon different type of the conditions. Okay, so how do we have discussed the how we can it will be translated and how it will, for examples also. Next, homogeneous coordinates. It is well known that many applications involve a sequence of geometric transformations. For example, an animation might require an object to be translated, rotated, and scaled at each increment of the motions. So, for example, if you want to first rotate an object, then scales it, you can combine those two transformations to composite the transformation like the following equation. So, many applications are learn the different type of the geometrical equations, transformations. In that way, whenever we have to define the animations that require the objects, so it may be translator, it may be rotator, it may be scaling. In the graphical representation may be most important to the translation, scaling, rotation. So how we can increment all the operations, then you are using to the from equation is a equal to s into r, that equal to sx0 0 sy of cos theta minus sin theta cos theta, that equal to sx cos theta minus sx sin theta sy sin theta sy cos theta. So based upon these two transformations, two composite transformations, like the different of the equation, that equation is that is sx cos theta minus sx sin theta sy sin theta into sy cos theta. Okay. Next, however, it will be difficult to deal with the above composite transformation and translations together, because translation is not 2 by 2 matrix presentation. Okay, so consider how the matrix representation discussed in the previous sections can be reformulated so that such transformation sequences can be efficiently processed. See, next is standard technique. That is the next one is the coordinate of the 3, homogeneous coordinate 3. Okay, so a standard technique for expanding each two-dimensional coordinate positions, it representation of x comma y to three element representations called homogeneous coordinates. So where homogeneous h is a non-zero value such that x equal to xh by h and y equal to yh by h. Okay, a convenient choice is simply to set h equal to 1. So each two-dimensional positions is then represented with the homogeneous coordinates of the x comma y comma 1. So based upon that values we can find the particular representation of the uh, homogeneous coordinate values. For example, if there is a non-zero value, that is x equal to x h by h and y equal to y h by h, whenever you are taking the h equal to 1, then the position of x equal, that is x comma y comma, and the constant value is 1. Okay, so likewise we have to perform the homogeneous coordinates. Okay, so for example, it is maybe x comma y from the tree representation, it is called as the homogeneous coordinates. Okay, so in the or 3 by 3 matrix representation, the translation is x dash y dash 1 equal to 1 0 tx 0 1 ty 0 0 1 into x y 1, and rotation x dash y dash 1 equal to cos theta minus sin theta 0 sin theta cos theta 0 0 0 1 into x y 1. We can go from the scaling x dash y dash 1 equal to sx 0 0 0 sy 0 0 0 1 into x y 1. Okay, so mainly when we resolve from the 3 by 3, actually you can take the 2 by 2, and here you can take the 3 by 3 matrix presentation. We have to perform these type of the operations, the translations, rotations and scalings. Okay, so why you are doing this is so that we can perform all the transformations using matrix or vector multiplications. This allows us to pre-multiply all the matrices together. The point of x comma y needs to be represented as x comma y comma 1. That is, this is called as a homogeneous coordinates. Now, how we can represent a vector of vx comma vy? See here. Next, composing the transformations. How we can compose the transformations? See, in the process of applying the several transformations in succession to form one overall transformation, so based upon that, we can perform the composing transformations. That is, we can apply the several transformations, then apply the several transformations, we can succeed with applications. If we apply transforming a point P using M1 matrix first and then transforming using M2 and then M3, then we have M3 into of M2 into of M1 into P. This is the P is the particular point of the transformation, M1 is the matrix 1, M2 is the matrix 2, M3 is the matrix 3. So based upon that, we can perform the equations and we can solve the, then we can apply the transformation, that is M3 into M2 into M1 into P. Okay, that equal to M3 into M2 into M1 into P. Now we can take all M3, M2, M1 in the M form of the M. Okay, then M into P, that is a pre-multiplications. See, matrix multiplication is associative, that is M3, M2, M1 equal to M3, M2 into M1, that equal to M3 into M2 into M1. So transformation products may not be communicate A cross B not equal to B cross A. So some cases where A cross B equal to B cross A, that is A is a translation, B is a translation, scaling, rotation, but A is the uniform scaling, but B is a translation, sorry, rotations. Okay, in that way, in different type of cases, it may be some of the A cross B equal B cross A equal to, but normally in communicative formula, that is A not B, A cross B not equal to B cross A, but some cases it will be equal, that is A cross B equal to B cross A. That is the translations, scaling, rotations are equal, but when go for the in the A is, you can say that uniform trans scaling, but here the rotations, so Sx equal to xy. See, for example, general two-dimensional pivot point rotation, that is xr comma yr. The next one is xr comma yr, then xr yr, then xr yr. So here the pivot point representation is whenever take scaling, can apply the transformation, it will be same. When apply the transformation, it will be rotate to the point, and it will be the translation, then it will be change the rotations. Okay, so we can generate a 2D rotation about any other point x comma y by performing the following sequences of translate, rotate and translate operations. So this is likewise we have to find the object xr and is the coordinate point 0 0, and it will be rotate, and it will be transformation, it will be places changed. Okay, for example, the translate object so that the pivot point position is moved to the coordinate origin, that is coordinate origin is 0 comma 0, Rotate the object about the coordinate origin. Translate the object so that the pivot point is returned to its original position, that is 1 0 xr 0 1 yr 0 0 1, that is cos theta minus sin theta 0 sin theta cos theta 0 0 0 1, that is and into 1 0 minus xr 0 1 minus yr 0 0 1, that equal to cos theta minus sin theta xr of 1 minus cos theta plus yr sin theta cos theta yr of 1 minus cos theta minus xr sin theta and 0 0 1. So therefore t of xr comma yr into r of theta into t of minus xr comma minus yr equal to r of xr comma yr comma theta. Next example of scaling, that is the scaling without translation. So translate the object to so that the fixed point coincides with the coordinate origin. So scale the object with respect to the coordinate origin. Use the inverse of the translation in step 1 to return the object to its original positions. Okay. See here, first one is the translations, then next one is the scaling, and next one translations. Now you can get the same position. So t of xf comma yf into s of sx into comma sy into t of minus xf comma yf equal to s of xf comma yf comma sx comma xy. Then 1, the matrix presentation is 1 0 xf 0 1 yf 0 0 1 into sx 0 0 0 sy 0 0 0 1, then 1 0 minus xf 0 1 minus yf 0 0 1, that equal to sx 0 xf of 1 minus sx 0 sy yf of 1 minus sy 0 0 1. Okay, the next one is the other transformation, that is sharing and reflections. Okay,